18. So lecture 18 is about inverse functions. We want to determine whether or not a function is a one-to-one function or not. So it has to be a function, or an equation has to be a function first before you want to check it's a one-to-one function. Later on, we want to determine the inverse function using a set of points or a table and equations, and obtain the graph of inverse function from the graph of the original functions. Okay. Now let's write down the definitions of one-to-one functions. So a function is one-to-one if no two inputs of the domain of f have the same output. So when I talk about functions, I give you the example that, okay, in the class we have multiple names and we can have multiple people born in the same month. Okay, so that function, but that example is not a one-to-one function. Okay. So a one-to-one function example is still an example. So relationship, right? So me and my wife, that's a one-to-one function. Okay, if there's a second person, not person occur in that relationship, it's no longer a one-to-one function. You got the example? Okay, that's a one-to-one function right there. Now, graphically, later on, we will work with algebraic method that we work with algebraic method to obtain or to check if a function is one-to-one function or not. But here, I want to show you a technique that you can check if a graph of a function represents a one-to-one function. Okay, it's called the horizontal line test. A vertical line test tells you if a graph is a function or not. A horizontal line test will tell you if a graph of a function represents a one-to-one function. Okay, so horizontal line test. So a function is one-to-one if and only if no horizontal line intersect the graph of the function at more than one point. So I have two graphs to example right here. They are both functions, right? We know that because when we apply vertical line test, right, put in the vertical line intersects the graph at only one point. So we can show that these two graphs are graph function. However, for the first graph, this is not a one-to-one function because when you put in one horizontal line, the horizontal line intersects the graph at 2 points. So it's not a one-to-one function. But in this case, this is a one-to-one function. That's no matter what horizontal line you put in, always intersect the graph at only 1 point. So here for the first graph, this is function. but not one-to-one. And on the second graph, this is functions and one-to-one. So when I say just one-to-one, I mean one-to-one function. So as I mentioned earlier, you have at this point two different tests, vertical line test and horizontal line test. So vertical line test. Using this, you check if a graph represents functions. And horizontal line test. You check if a graph of a function is one-to-one. So we want to know if a function is a one-to-one function because that's a very important conditions. Because when you find inverse functions, only one-to-one function can have an inverse. You would mean that. Okay. That leads us to the next concept, the inverse of functions. So let f be a one-to-one function. With domain A and range B. Then its inverse so here is the notation. And you have to be very careful with the notations. The inverse is f -1. This is not f to the -1. No, it's not. This is not 1 over f at all. Okay. When I say this, f, I say f -1 or f inverse. Okay. It's not f raised to power -1. No, it's not. It's f inverse. Now the inverse has domain B and range A. So the original function you have is f. The original function has domain A and range B. And when you have the inverse, when you find the inverse has domain B and range A. And is defined as f inverse of y equal to x or f of x equal to y. So this notations means if and only if. So a quick note here, again, domain of F will become the range of F inverse. And the range of F becomes the domain of F inverse. So far, so good. Yeah. Okay. Let's start with example 2. In this case, you have some inverse function. Sorry, it's one-to-one function, and you want to find the inverse of the one-to-one function. So A and B are the set of points, and they are one-to-one functions because no two inputs go to the same output. Okay. So one input corresponding to exactly one output, no two input corresponding to the same. Okay, so these are one-to-one functions. Okay. What we want to do is we find the inverse of the one-to-one functions. Another task that we need to do is define domain in range of inverse. So to find the inverse of one-to-one function is very simple. X become Y, Y become X. That's it. So the inverse functions is going to be, so the first point becomes -27, -3. The second point is -8, -2. The third point is -1, -1. The fourth is 0, 0, and then 1, 1, 8, 2, and 27, 3. Because we are working with a set, that's why the result has to be written inside a curly bracket. Now the domain of the inverse is going to be -27, -8, -1, 0, 1, 8, 27. So these are dear. So in the last in exam 1, some of you write the answer as from -27 to +27. Similar to that, right? Which is wrong because these are discrete points. So you have to count one point at a time. It's not a continuous point. Oh, sorry, not continuous function. So this is discrete function. Again, you have to count one point at a time. So what because of that, when you write the domain of the inverse, you have to write down one number at a time. It's not indivisible integer. Okay. So now move on to the range of the inverse. You have -3, -2, -1, 0, 1, 2, 3. All right, so that's problem A. Any questions? Good. Now problem B. The inverse going to be
negative 15, comma 4, negative 18, comma negative 8, negative 16, comma negative 2, and 15, comma 3.
Again, when you find the inverse for this type of problem, the discrete functions, so y become x, x become 1. Right? And we will see why that is the case later, why you just need just one x and y.
Now, the domain of the inverse
So you have to list all the numbers starting from the lowest number to the highest number. So in this case, the x value is not really in order, so, but still, when you write the domain of the function, you have to write from the lowest number to the highest number. So negative 18, then negative 16, negative 15, and then 15.
and similarly for the range of the inverse. You have to start with negative 8, then negative 2, and 3, then 4.
Any questions on B? Now for problem C and D, it's going to be very similar to A and B. But in this case, everything's written in terms of the table of values. All right, so you have x, you have f of x. So these are just one-to-one functions. Now you want to write them in terms of inverse functions. So what is the x value? What is the inverse of the x value? So x become y, y become x.
So you have 0, 2, 4, 6. The inverse 4, 5, 6, 7. And again, you're going to write the domain of the inverse. Is a 0, 2, 4, 6. And the range of the inverse is 4, 5, 6, 7.
Now for D, it's going to be the same. X becomes y, y become x. For the inverse, you have 5, 4, 3, 2. And negative 3, negative 2, negative 1, 0. So the domain of the inverse is 2, 3, 4, 5. Again, you have to write the set, the value starting from the lowest number to the highest number. So that's why you start at 2 and end the set at 5.
Then the range of the inverse is negative 3, negative 2, negative 1, 0.
Okay. So with this 4 example, with this 4 problems, hopefully you get some idea how to obtain the inverse from your regional functions using a set, a point, or the table values. Now we're going to move on to graph of an inverse functions.
So the graph of an one-to-one functions. And the graph of its inverse are symmetrical with respect to,
so WRT again is with respect to
the line y equal to x.
because of this, you find the inverse, you just basically switch X and Y. So I have an example here. The original graph is the one-to-one function of x cubed. And the inverse of x cubed is cube root of x. So the graph in blue and the graph in red are symmetrical with respect to the line y equal to x because they are inverses of one another. Good. Okay. Now in example 3, you're going to match the graph on top of the graph with the corresponding graph in the bottom here. You have 3 different one-to-one functions. Okay. Can you match the graph of the inverse? Remember, the graph of the one-to-one function and the graph of its inverse is symmetrical with respect to the line y equal to x. All right. So what is A corresponding to? What do you think? Yes.
This one, no one, I,
I. Okay, so A go with I.
one,
What about B? All right. So remember, is the line y equal to x, right? This is the line y equal to x, and this is the line y equal to x. So what is B corresponding to? It's actually 3. Okay. Like that. So B3 and C2. I'm very glad that I typed everything out. Like, otherwise, I cannot draw it at all. Do you see the corresponding graph between the original function and the inverse? So again, the graph corresponding to or symmetrical with respect to the line y equal to x. So that. So A1 beats 3 in C2. So now, so far, we find inverse functions using a set, right, using table of value, using graphs. Now we're gonna move on to finding inverse functions of the original function algebraically. Okay. Now, before we do that, we need to check one thing, this is the inverse function property.
Or there's another name, it's called cancellation property. Let f be a one-to-one function. The inverse function f inverse satisfy the following cancellation properties.
Right, so there are two formula.
F inverse circle with f or composes with f of x, or f inverse of f of x has to be equal to x. And f composes with f inverse of x, or f of f inverse of x equal to x.
So why they are called cancellation properties? So this, what I'm about to say is not mathematically correct to say, but it's very convenient for us to understand the concept. This is called cancellation property because you can see here, f inverse and the original function, they kind of cancel out and you're left with just x. You see what I'm saying? Okay. And again, here, f and f inverse, in this context, they cancel out and you're left with just x. Again, this is not mathematically correct, but when you look at that, it's easy, it's convenient for us to understand the concept. To actually show that f and f inverse are behave like it is right now, can follow satisfy the cancellation property, you have to work out the details to show that when you do composition of these two functions, you end up getting the value x at the end. All right, so that's led us to example 4. Can you verify that the inverse g of x equal to x to the third power and the inverse cube root of x are inverses of one another? When you perform these calculations, the answer should be x. Okay,
So here you do g inverse composed with g of x, or g inverse of g of x. You got g inverse of x cubed.
Right, very similar to what we did yesterday when we do composition of functions. Any questions up to this point? Okay. So g inverse is q root of x. You take out the x and you replace by x cubed.
Right, so q root of x, right? But again, you take out the x and you replace by x cubed.
Now cube root with x cubed, right, or cube root with the third power, they cancel out and you're left with just x. So that's the first cancellation property.
Now the second cancellation property, g composes with g inverse of x, or g of g inverse of x. or g of q root of x.
Right, so g of x is x cubed. You take out the x and you replace by q root of x.
So let me do this. All right, so this is x cubed, right, for g of x. But what we are looking for is g of q root of x. So you take out the x and you replace that with q root of x.
Now again, the cube root and the third power cancel out,
And you left with just x.
Any questions? We good? Okay, so that's how you check if the two functions are inverses of one another. Let's move on to example 5. It's very similar concept. Similar approach here. You check the two cancellation properties.
That's f inverse circle with f of x, or f inverse of f of x. F inverse, so f of x is equal to 2x minus 3.
And f inverse is 1/2 times x minus 3.
So what you do is you take out the x and you replace by 2x minus 3. Then another. Sorry, 2x plus 3. Sorry. Then minus 3.
All right, so f of x is 2x plus 3.
And here you see that 3 and negative 3 cancel out. And you're left with 1/2 times 2x.
And 1/2 times 2 becomes 1. You're left with x at the end. And again, to show that f inverse and f are inverses of one another. Then we're going to move on to the second cancellation property.
F circle with f inverse of x, or f of f inverse of x. So f inverse is 1/2 times x minus 3.
And f of x is 2x plus 3. So you remove x and you replace that by 1/2 times x minus 3.
So 2 times 1/2 times x minus 3, and then plus 3.
Now 2 times 1/2 becomes 1.
And you're left with x minus 3 plus 3.
Negative 3 and 3 cancel out. You're left with just x. Any questions? All right, example 6. Again, similar concept. Gonna check two cancellation properties.
So f composes with f inverse. Right. You have f of f inverse of x.
For f inverse is 1 over x plus 1. And f of x is 1 altogether over x minus 1.
So 1 over.
So you replace x by 1 over x plus 1. So 1 minus 1 becomes 0.
And you're left with 1 divided by 1 over x. When you divide your fractions, then you can multiply by the reciprocal. You get 1 times x over 1, or this is x. Right. Now another one here, f inverse circle with f of x, or f inverse of f of x. For f of x is equal to 1 over x minus 1.
Now for f inverse, you have 1 over x altogether plus 1. So in that case, you remove x and replace by 1 over x minus 1.
So here's the calculations. So 1 over x, right, plus 1. So that is for f inverse. What you do now, you replace x by 1 over x minus 1.
Right. Hopefully, these two calculations show you that there is different approach on getting the x, right? So you have to be careful when you do. So here, for the first term, 1 over 1, x over x minus 1, you divide a fraction, you multiply by the reciprocal. For this first term, we haven't touched the second term. Right, so this one becomes x minus 1.
So 1 times x minus 1 over 1 plus 1, or x minus 1 plus 1 equal to x.
Any questions? Good. All right. Now we move on to the last topic is that we're going to find the inverse of the functions algebraically. Okay. So there are certain procedures that you need to follow to get to the inverse of the one-to-one functions. So there are 4 steps. The first one is very simple. Just write y equal to that particular one-to-one functions. The second step is to solve for x in terms of y. And then later on, we just interchange x and y. And remember, we can do that because the inverse, the one-to-one function, and the inverse are symmetrical with respect to the line y equal to x. So just interchange x and y. And then the resulting equation is the inverse functions that you're looking for. You good? All right, okay. Let's start with example 7. So this function, this given function, again, is a one-to-one function. We want to find the inverse of this one-to-one functions.
So the first step is write y equal to that function. So that's the first step, right? So write y equal to f of x.
Now, the second step might involve or the step in manipulations as well. That is to solve for x in terms of y.
Right. So that means I want to extract x or solve for x by itself. I want to get x by itself. So what you do next is to multiply 2 for both sides of the equations, and you get 2y equal to 5 minus 3x.
Now, again, the goal is to solve for x by itself.
You move 5 to the left-hand side, you get 2y minus 5 equal to negative 3x.
And then to get x by itself, I divided both sides for negative 3.
And I get 2y minus 5 over -3 equal to x. So this three smallest step is just for you to solve for x in terms of y. Now the third step is to interchange x and y. So x become y become x. So here you got 2x minus 5 over -3 equal to y. So you just interchange x and y. So now 2x minus 5 over -3 is the inverse that you're looking for. So f inverse of x is 2x minus 5 over -3. You can leave the representation of the function this way, or you can rewrite it in terms of -1/3 times 2x minus 5. Or you can distribute -1/3 into the parentheses, and you get -2/3 x plus 5 over 3, right? Either form should be fine. Just want to get to the point that this function is the inverse of the original function. Yeah. Good. Good. So there are 4 steps again. First, they give you the one-to-one function, just write y equal to that function. The second step is to solve for x in terms of y. And then the third step is to interchange x and y. Then you get the answer at the end. Example 8. You want to find the inverse functions of f of x equal to x squared for x greater than or equal to 0. So you need the condition x greater than or equal to 0, otherwise not going to work. Why that is the case? So here you remember that y equal to x squared is the parabola. That's the quadratic function graph is the parabola. Up here. So for x squared, this is x, this is y, this is the parabola, right? So if you consider the entire parabola, this is not a one-to-one function because of the horizontal line test. You with me on that? Okay. Therefore, you need the condition that x is greater than or equal to 0. So you just need one wing, right? Just the part of the positive part of, or the non-negative part of x. So the graph should just be this. Now that is a one-to-one function, right? So this is y equal to x squared for x greater than or equal to 0. Therefore, this is a one-to-one function. So you start out by writing y equal to the function x squared. Now, next step is, okay, this step is write y equal to f of x. The next step is to solve for x by itself. To get x by itself, you basically just take the square root on both sides of the equations. When you do that, remember you're solving equations, therefore you have 2 solutions, right? Plus and minus square root of x. So x equal to square root of, x equal to square root of y, or x equal to negative square root of y. But remember the condition. But what we have is x greater than or equal to 0. Therefore, you just need the positive part of the square root. So x is equal to square root of y. So what we just did is solve for x in terms of y.
Now the next step is to interchange x and y.
Right, so x become y, y become x. So here you write y equal to square root of x. And you interchange x and y.
And that is the inverse functions that you're looking for.
So then y equal to positive square root of x. Let me write this. F inverse of x is equal to square root of x for x greater than or equal to 0. Is the inverse of the function y equal to x squared for x greater than or equal to 0.
Any questions? Good. All right. So we have two more examples for this lecture. So let me do example 9. And then for example 10, I will record a video and post that on Blackboard. So example 10 is a little bit more involved as the rational function requires multiple steps in order to get to the inverses. So it's harder, so I need more time for that particular example. All right, so example 9, find the inverse functions of f of x equal to x cubed plus 2. So in example 8, you have, this is called the even function because of the even power, right? And also the graph, because of the even function, the graph is symmetrical with respect to the y-axis. Right? Therefore, when you consider the inverse of this even function, you need to impose a condition so that you have a one-to-one function. However, when you get to x cubed here, in this case, plus 2, you don't need the condition because x cubed is an odd number, right? X cubed is an odd function. Okay. Therefore, you don't need the conditions to show that this is the inverse, is a one-to-one function already. So to find the inverse, first you write y equal to x cubed plus 2. So you write y equal to f of x. And the next step is to solve for x by itself or to solve for x in terms of y.
To get y minus 2 equal to x cubed.
And to find x by itself, you take the cube root on both sides of the equations,
and you get cube root of y minus 2 equal to x. So basically, you just solve for x by itself. So for x in terms of y.
And the next step is to interchange x and y.
So x becomes y, y becomes x. So you get cube root of x minus 2 equal to y. Here you interchange x and y. Then you can conclude that the inverse functions of f of x equal to x cubed plus 2 is f inverse of x equal to cube root of x minus 2.
So now let's take a look at example 10. So again, in this example, we're looking for the inverse functions of the rational functions to x plus 1 over x minus 1. And again, I want to remind you the procedures that we need to follow in order to obtain the inverse functions of this original functions. So the first step is to rewrite the function as y equal to f of x. And then the second step is to solve for x in terms of y. And the third step is to interchange x and y. So x equal to y and y equal to x. And then the resulting equation is the inverse function that you're looking for. Okay, so in this case, you get y equal to 2x plus 1 over x minus 1. So again, this one is the step where you just rewrite y equal to f of x. And the second step is for us to manipulate the equation so that you can solve for x by itself. So the first step is to cross multiply x minus 1 or multiply both sides of the equation by x minus 1. So y times x minus 1 equal to 2x plus 1. So the next step is to distribute y, and you get x times y minus y equal to 2x plus 1. Now try to group everything related to x on one side of the equations and everything else without x on the other side of the equations. So I'm going to move 2x to the left-hand side and negative y to the right-hand side, and I get xy minus 2x equal to y plus 1. Now, on the left-hand side, you have all the terms related to x or with x attached to it. So you take x as a common factor. You have x times 2y minus 2 equal to y plus 1. And to get x by itself, you divide both sides for y minus 2. And you get x equal to y plus 1 divided by y minus 2. So for this steps, you actually solve for x in terms of y. Now, the next step is to interchange x and y. So y becomes x becomes y. So here you get y equal to x plus 1 over x minus 2. And this is the inverse functions that you're looking for. Okay, so this is interchange x and y. So therefore, you say that the inverse function is y or f inverse of x equal to x plus 1 over x minus 2. Now, if you are extra careful, you can find the domain of these rational functions, and the domain of the inverse is all real numbers except 2. And so except 2. And it could be very good if you find the domain of the original functions as well. So in this case, the domain of f is all real number except 1. All right. So this is finding the inverse function of a rational function. So I hope it's helped, and this concludes our lecture on inverse functions. So in this lecture, we cover a few topics. We cover how to define a one-to-one function. So again, one-to-one function is a function where no two inputs of the domain of f have the same output. And graphically, you can identify the graph of a function to be a graph of a one-to-one function using the horizontal line test. We wrote down the definitions of the inverse of a function. So in order to have an inverse function, the function has to be a one-to-one function. So we cover some example how to find the inverse function of the one-to-one function in terms of a set of points, in terms of table of values, and we use graph to find the inverse. So the graph of a one-to-one function and the graph of an inverse function are symmetrical with respect to the line y equal to x. And toward the end, we find the
we find the inverse functions using algebraic method. Okay. In order to check if the two functions are inverses of one another, we need to check the two conditions in the cancellation property. So again, that concludes our lecture. Please let me know if you have any questions.